Okay. I've got the recording on. Apparently last week's recording didn't have sound for some reason. I don't know what to say about that, except that I tested this literally 20 minutes ago and it has sound. So we're going to find out if I've done this right or if I'm just super unlucky. I think I've also got the chat in there now too. All right. So before I start, any questions about the homework or the lab or the anything like that so far? Okay, let me crap, I dropped my mouse. Let me open these up. And I don't remember what number 6 is, so let me get it and I will Okay. We're going to talk a little bit about the addressing stuff today, but generally speaking, actually, yeah, let's start this way. If you think of a computer as having a memory chip, okay, and just like on a street, you have houses. Look at these awesome houses I'm drawing, guys. Those are all houses. And every house has an address, okay? And the address is a numerical way to talk about a house and to keep them separate and to deliver mail to one house and another house and that sort of thing, okay? A memory chip is a bunch of slots. Each slot holds 1 byte worth of stuff that's all zeros and ones. So maybe this one has all zeros, this one has all ones, and so I'm drawing that really small because I drew my cells too small. But you get the idea, right? Okay, each one of these cells is 1 byte in memory. Okay, every one of those bytes in memory has an address, a location. So these guys are the contents of memory, and these guys are the addresses of memory. The addresses are the locations of the actual things in memory. Okay? So what question 6 asks is, it says, so let me write question 6 slightly differently. If I have 6 gigabytes of memory, I don't know if I ever officially told you this, but 1 kilobyte is around 1,000 bytes. It's a little bit more because it's really 1,024 because the powers are 2, but you'll be fine with this. 1 megabyte is around 1 million bytes. 1 gigabyte is around 1 billion bytes. Okay? So, and then I think terabytes the next one, and that's trillion, and so on and so on and so on. What the question's actually, so another way of saying if I have 6 gigabytes of memory, another way of saying that is I have 6 billion cells. 6 billion slots in memory. Every slot needs an address. Okay? So I need 6 billion different addresses. Okay? So I'm not going to draw them all, but imagine if this chart up here had, instead of 0 through 10, 0 through 6 billion. And nobody wants to watch me draw 6 billion things, so I'm not going to. But if I did that, then I'd have a spot for 0, and a spot for 1, and a spot for 2, and a spot for 3, and a spot for 4, a spot for 10, a spot for 100, a spot for 1,000, a spot for 9,473, a spot for 8,396,912, and on and on and on and on and on, all the way to 6 billion, right? So I need a way to store numbers from 0 to 6 billion. Okay? So what the question's really asking is, how many bits do I need to store 6 billion combinations? And so all it's really doing is giving you a real application for the second awesome formula of doom, which was, so the answer to this is going to be, so recall the awesome formula of doom, which said that log to the base 2 of number of combinations is number of bits you need. And so all I was trying to do is give you kind of an address-based, memory-based use of a way to get you at this question. Okay, so what the question is really asking is, I have to store all of the addresses, all of these numbers from 0 to 6 billion in one place. I need, how many bits am I going to need to do that? What 7 says is, suppose I allocate 4 bytes, so 32 bits to my address. So 6 should be so it turns out log to the base 2 of 1 billion is 30, of 2 billion is 31. It doubles every time. Of 4 billion, that's 4, is 32. So I think you need, it gets up to 8 billion for 33. So 32 bits get you 4 billion combinations, which is not enough. 33 bits get you 8 billion combinations, which is too many, but you need to over allocate rather than under allocate, so you get all the combinations you need. Okay, so that's how you do 6. 7 says, what if I only had 4 bytes? 4 bytes is 32 bits. Now how many things can I address? Number 8 says 33 bits is not a multiple of 8. If I need to use full bytes and have the number of bits I allocate for the address be a multiple of 8, what's the smallest multiple of 8 that I could do? And number 9 says, hey, look, now that you have 5 bytes and 40 bits for your address, how many addresses do you really have? And so that's what I'm trying to get you to go through for those steps. Does that help a little? Maybe? Any other questions on that? Going once. Going twice. All right. So if you do have questions, ask me by email or ask me by whatever. You do not need to hand in the lab. The lab is there to teach you the stuff you need to do for the homework. And like this week, um, the homework will have hand in some stuff for the labs explicitly written as homework problems, and that's how you'll know if I want you to actually do part of the labs as the homework. Um, so all I need is the homework. If the homework wants part of the lab, the homework will tell you. If you want to show me your lab to have me check it over and make sure it's right or that you're doing the right stuff, that's fine and good, and you should be doing that. Especially if you're confused. The downside of seeing you guys, twice a week, it feels like as much time as a regular class, but keep in mind this is a 5-week class, so twice a week is really kind of like less than once a week if this was stretched out to a regular semester. 10 times. We're seeing each other 10. We're seeing each other. We're meeting together 10 times a semester, which is less than once a week if this was a real regular semester class. So see me more often than that if you need it. All right. Any other questions about the homework or the lab or anything? I'm going to post the new homework today and the new lab today. I'm going to try to get you guys up to a point where you can do that now. But if you got anything you want to ask, now it's time to ask. Okay. How do I? There we go. So today, what I want to do is talk about. So we've been doing how to interpret data or bits. So remember, if I say to you, what is some random bit pattern, and what does that mean? The answer is always it depends, because it depends on how you interpret it, right? So we've seen how to interpret it as unsigned integer. I've seen how to interpret it. Oops, I can't spell. To use complement, signed integer. We did a little bit of signed magnitude. I mentioned probably ASCII character. One thing the lab is trying to make clear. I guess I'll add this as an also. It could be interpreted as a location in memory, and those locations tend to be numbers, but they don't have to be. We tend to refer to slots in memory by an address number, and so every location in memory has an address number, and then there is the stuff at that address, just like your house has an address number, and then there's the stuff at that address, namely your house. The big one that I want to do today is to talk about how another thing you can interpret bits as, is as programs or instructions for the computer to follow. Okay, so I'm gonna try to start. Okay, computers can do only a few very simple tasks. They can do basic arithmetic, like adding. They can compare two numbers and see if they're equal or less than or greater than. And they can move data around. And that's about it. Which sounds weird given how much crazy big stuff a computer can do, but all of that crazy big stuff is really basic arithmetic, comparing two numbers and moving data around, combined in fancy ways with lots and lots and lots and lots and lots of combinations of these things, millions and billions, to get big complicated stuff done. Okay, we're not going to talk about it in this class, but it's worth noting since a computer is an electronic device, these basic tasks are implemented as electronic circuits. And so I'm not going to tell you how it works, but it's possible to create an electronic circuit that takes in a bunch of wires that have ones and zeros on them, because this is why binary numbers do the thing they do. One means there's electricity on the wire, and zero means there's not electricity on the wire. Do something in here that's some complicated bunch of circuitry. Take in another set of wires, and then in this complicated bunch of circuitry, spit out a sum that is whatever the sum is of those two numbers. Okay, how that works, you don't need to know, but do know that when I talk about the basic instructions a computer does, I'm talking about it using electricity to do those things. And the reason why we don't have a basic command for, I don't know, square root is because if we did, we'd have to have a circuit that figured out square root, and that's hard. So what a computer really does is have a few relatively simple circuits to do a few relatively simple tasks, and then do those tasks over and over and over again in some combination. Okay, so an executable program, if you're a Windows person, we're talking about .exe files. An executable program is a series of machine instructions. A machine instruction is basically a binary number that gets translated into a command for a circuit to do something. So I don't know if you've ever accidentally opened an exe file in like a word processing document or something like that. But if you ever have, what you see is a giant pile of nonsense. And what the nonsense is your word processing document trying to take the zeros and ones that are meant to be interpreted as machine instructions for commands to get Circus to do things, and trying to turn them into letters and characters and stuff like that in a word processing document. It gets all messed up. But the point is, this is what happens, partially what happens if you try to interpret a binary number meant to be done in one way in a different way. You get weird stuff that doesn't make sense. It also shows that these programs exist on the disk as binary numbers, just like everything else. And those binary numbers are meant to be interpreted as commands. Okay? So when a program runs, the instructions go into memory just like data does. So remember that chart I had before. I'm going to make a new page. Remember that chart I had before? I'm going to draw it vertically now instead of horizontally, of memory. Okay, and they all have different addresses, and these are the addresses of memory. This is a very, very small memory that only has 8 things in it. Some of these numbers are binary numbers that are instructions. Some of these are binary numbers that are data. And they both sit in memory, the same memory, just at different locations. And it's up to the processor to keep track of what goes where. Okay? So the processor is the part of the computer that does 2 main things. One, figure out what instruction to do next, and 2, do the circuitry for the instruction. So the processor is the part of the computer that figures out what we're going to do next and then actually does it. Okay, the processor is the part of the computer that actually computes. I would say the processor is a separate thing from the memory chip. I would say the processor is a separate thing from the disk drive. I would say the processor is a separate thing from the keyboard and the screen and all that stuff. The processor tends to be very, very small. I would say this is kind of about the size of a processor, like life size. The rest of your computer, so you're looking at a computer right now on a screen, somewhere in there is something about that size that's actually doing all of the computing. Everything else is helpers. The keyboard and the screen are sending information to it and taking information out of it and displaying it to you. The memory chip is storing data and instructions for memory. The disk is storing files, and the network is letting you hear what I'm saying. Do the circuitry. C-U-I-T-R-Y. Circuitry. Can I erase? I think I can. Circuitry. So the processor part of the computer is the part of the computer that actually does the steps and runs the programs and manages everything. Everything else helps it out. Okay, so to help the processor do this, it has special memory locations called registers. All a register is special memory wired into the processor. Most instructions use registers. And the registers have numbers. There's a register 0 and a register 1 and a register 2 and so on and so on and so on and so on. Most important register is called the program counter, which many people like to abbreviate as PC, program counter. What the program counter does oh wow, what did I just do? It holds the address of the next instruction to do. Okay, so here's what I'm trying to say, all right? How a computer works in 3 lines, okay? What a computer is doing as it's living its life, whenever it's turned on, over and over and over again, is first of all, the program counter holds an address. The second thing that will happen is get the data at that address. Remember, addresses are locations. Locations hold data. Okay, so the program counter is a number that is a location in memory. We go out to memory at that number and see what data is there. Okay. Interpret that data as an instruction. We'll talk about what that means in a minute, but instructions are also zeros and ones. do it. So do the instruction, which basically means activate the correct circuitry to do the correct thing that the instruction was telling us to do. Set the program counter to the address of the next instruction. Almost always, that's going to be the instruction in memory right below the one you just did, but not always. And then 6, do step 1 again. So this is an algorithm that, for how a computer does its job, and the computer will just keep on doing this over and over and over again until you turn it off. Okay? So what a computer does, and all a computer does, is load an instruction out of memory, interpret that instruction, that binary number it loaded as an instruction, using some kind of method that we'll talk about in a second. That instruction activates circuitry to do an add or a move data around or whatever, and then we update the program counter to point to the next instruction, and then we start all over again. Okay, this whole sequence of events. Oops, wrong way. Is called the fetch execute cycle, and it happens millions of times a second. Just as I was typing, this as I was writing that sentence, it happened millions and millions and millions of times for millions and millions and millions of instructions at millions and millions and millions of different addresses, cycling through over and over and over again. Okay, so that's what a computer does. Okay, so does that kind of make sense? The idea behind the fetch execute cycle, that we have the address that stores an instruction, and the instruction gets done in circuitry, and then we just keep on doing that over and over again. Now, the next question is, so how do I get these instructions that do the right thing? And we'll talk about that. But before I go there, you kind of get the basic idea. Questions on this so far? Got it. I like that. All right. Cool. All right. So the next question then is, so how does the computer interpret a number as an instruction? So remember, the fetch execute cycle said the program counter holds an address. The address is out of memory. The data at that address is the thing I want. And that's the thing I'm going to do. Okay. Basically, each computer, each type of computer has its own what's called machine language. A machine language is a way of interpreting bits as instructions. And different machines do it differently. Yes, exactly. So the reason why you can't really run a Mac program on Windows without going through a lot of weird gyrations and stuff is because the Mac machine and the Windows, the Intel machine, I guess that's really the processor underneath, have different machine languages. And if you try to feed a program that has binary numbers that are instructions for a Mac processor to a PC, it's going to be like, I don't know how to do this, and it's going to interpret the instructions wrong, and it's going to freak out, and it's not going to do. It's going to crash. So this is why it's hard to run the same program on different types of processors. Not impossible. There's ways to translate, but hard. And this is why most of the time when you download something, it asks you if you're downloading it for a Mac or for a PC because it's giving you different sets of executable files that have probably similar instructions, just written in a different machine language. Okay, it's why the iPhone and the Android apps are not directly compatible, and you have to get the right thing for the right kind of phone because even your phones are just computers that have processors in them that have their own machine language. And you can't run Android stuff on an iPhone, and you can't run iPhone stuff on an Android. You can't run a Windows executable on an iPhone, even though they're all just computers under the hood. It's all about the different machine languages. And so, because there's not one standard machine language, the way there's one standard way to interpret binary numbers, we have all of these different kinds of programs written in still in zeros and ones, but different interpretations of zeros and ones. Okay, so that's the idea. Okay, so some programs are compatible with different machines. Now there's a couple of different things going on there. First of all, like for example, the lab last week made you do that binary number converter, and everybody, once you got your Java thing working, was able to run it in the browser, some on Mac, some on PCs, some on whatever. And that's because Java itself is able to translate commands written in Java on the web page into whatever machine language it's sitting on. So the way a Java applet works is you have your applet and it talks to your underneath Java, and your Java translates into machine language on the fly as you're running. Um, so so what ended up happening is when you install Java on your machine, you had to install the right kind of Java for the right kind of machine you were running, so that it knew what machine language it was trying to turn the applet into. Okay. Other programs are compatible on different machines. Macs tend to know how to run PC stuff. They can kind of translate machine language on the fly sometimes. Some other things, you can get translators. Some programs really are automatically downloading the correct machine language version. I'm running this chat thing in Firefox, and I have a Firefox for Mac and a Firefox for PC. They're both the same program, but you're downloading the correct version that is written in the correct machine language. So there's lots of ways around this, but they are ways around it. They're not things that just happen naturally. Okay, so yeah, if I write a program and stick it in the machine language of a PC, it's not necessarily obvious it's going to work on every machine in the world. So yeah, cool. All right. So as a way of making you see this and experience it for yourself in all of its painful glory, the book defines a simple machine language. This week's lab and homework is playing around with it. So I want to show you kind of how it works now, so that when you go off and do it on your own, you can understand what it's talking about. I think I wrote the lab in a way that if you just follow the instructions, it'll make sense. But having me here ought to be helpful. So let me try to bring this up. I got to figure out a way to share the right part of my screen. Woohoo. There it is. All right, can you guys see kind of a gray and bluish window pop up there? Okay. Let me make sure it's recording. Yeah, it looks like it is. All right, so when you run it, this is what you're going to get, okay? And what you're seeing is, I don't know if you can see the words or not. Over on this gray box, the things I'm highlighting now are the registers. And so this machine has registers from 0 to 15. It's written in hexadecimal, so 15 is F. And it's got a program counter where the program counter is telling you when you run this what instruction in memory, and then memory is the blue part, am I going to do next? Okay. The way you write a program is you put an instruction, which is going to be 4 hexadecimal numbers. I don't know why this is only showing me 3 of them at a time, but there really are. Let me do this. 2, 2, 1, 3, 4. 1, 4, 5. So 2. Hopefully this is not too small. I don't know how to change the font in this. Is there a way to increase the font size? No, fortunately. So the lab walks you through exactly what the bit patterns mean and what the instructions mean. But if I type in 2145, it tells me here, load register 1 with bit pattern 45. Okay, so so this is what you should see, and then when you run it, what ended up happening there was the program counter was actually, let me reset this. Step means do one instruction at a time, one cycle through that fetch execute cycle at a time. So what step does is it steps through the first instruction. It turns out that 2145 means load register 1 with bit pattern 45. And so after doing that, register 1 has changed to have a 4-5 in it. See that? And the program counter has automatically got bumped up to 02. And if I had an instruction at memory address 02, it would do that. Okay? It doesn't, so when I step again, I get an error at the bottom saying, I don't know what to do, program stopped because you didn't give me an instruction there. But the point is that this is a program, okay, written in a machine language. It's not the Windows machine language. It's not the Mac machine language. It's not any machine language that exists on an actual computer. It's way, way simpler than that, okay? And so what you want to see is that I want to get back. So I'm going to minimize this again just for a second and share my writings again. Come back here, you green arrow. Okay. So, things to notice about that the lab is going to walk you through, but I want to kind of talk to you about it now while I have you guys here. First of all, an instruction is 4, always 4, not 3, not 5. Hexadecimal digits. Okay. Every instruction you would write in this machine language is 4, not 3, not 5, not 7 hexadecimal digits. And what that means is, since a hexadecimal digit, hexadecimal digit, is 4 bits. Remember, the whole reason we have hexadecimals is a compact way of writing 4 bits as one thing. That means an instruction is 16 bits, 4 times 4, or 2 bytes long, right? The second thing to notice is, so each instruction is placed at an even memory address. So this is why that chart, let me put it back. This is why the chart of how do I get you back? Of the machine here. Yeah, goes to 2. Right. So this is why it's 0, 2, 0, 4, 0, 6, 0, 8. 0A is 10. 0C is 12. 0E is 14. 1, 0 is 16. And on and on and on. Because this is memory, and every instruction takes 2 bytes. So every instruction, it's listing out all of the 2-byte slots for you here as it goes down. Okay? So every instruction is 2 bytes. And so every instruction goes at an even address. The program counter, by default, where is the program counter by default so 2A. The program counter will go up by 2 after each instruction because every instruction is 2 bytes long. There exists unless you're told to go somewhere else. You have the ability, there exist instructions that say, instead of doing the next one, go do this one instead. And that's a way to make your program do steps over and over again, to do steps based on different conditions and things like that. The second half of the lab walks you through that kind of stuff. The third big thing is the 4 different hexadecimal digits all have meaning. Okay, so it really does help to think of it as hexadecimal, not as binary for this machine, because everything is done hexadecimally. And the first of the 4 hexadecimal the first of the 4 hexadecimal digits is interpreted as describing the type of instruction to do. So the first of the 4 hexadecimal digits is, here's what I want you to do. Here's what instruction I want you to do. Here's the command I want you to have. The official word for this is called opcode. Stands for operation code. But the point is this. Let me go back and try to load this thing again. Where are you? Woohoo, green arrow. Wish I could share 2 different screens at once. The reason it knows that 2145 is load register 1 with bit pattern 45 is because 2, instruction number 2, means load a register with a bit pattern. Instruction 5, I think it is, means add the numbers in 2 registers together. Number 3 means save a bit pattern from a register out to memory. Okay, I don't even know what some of these are. The hexadecimal ones exist. Not that so rotate the bit pattern to the right, and all kinds of weird stuff. The point is that the way the computer knows what to do, the way the computer knows how to interpret these 4 hexadecimal digits as an instruction, is it interprets the first hexadecimal digit as an operation, as a thing to do, okay? And then the rest of it depends. Screen share. The other hexadecimal digits. Opcode, yes, OP, opcode. The other hexadecimal digits do different things depending on the instruction. So the way we interpret the second, the third, and the fourth hexadecimal digit depends on what the opcode was and what we're trying to do. Okay, but there is always, whoa, what did I just do? There is always 4 hexadecimal digits. So if you find yourself trying to write 3 or 5 or something, you're doing it wrong. And most instructions refer to at least 1 register by its number. So the lab walks you through defining what a bunch of instructions are, and I write it as a chart. So the chart has 4 spots, and it's like, if the first digit is 2, then instruction is put a number in a register. Second digit means the register. 3 and 4 mean the number. So again, the lab will explain this better. But I wrote the lab as, you know, at least when I show you new instructions in the lab, I wrote it as kind of a chart where the first thing you care about is the first digit because that's telling you what to do. And then when you see that first digit, you know what you're supposed to do, at least in terms of what's supposed to happen in the computer. And then the rest of it is how to interpret the rest of the digits of the hexadecimal number. Okay, so I wrote the lab as kind of two main parts. Part one is what I would call simple instructions. Now, obviously, none of this is simple, right? You're probably freaking out thinking about all this hexadecimal and instructions and binary numbers and all this program counters and all this crap. But it's instructions that just move data back and forth, does basic adding and things like that. Make sure you finish part one, and I would even do a couple of the homework questions and then go away for a day or two and let this sink in. And then come back and do part two, which is basically messing with the program counter. The idea that instead of making the program counter walk through your program top to bottom, one thing at a time, that we can do stuff to it, and that lets our program make decisions, that lets our program do certain steps over and over again, and that sort of stuff. But that's really only going to make sense if you get and can write programs using the basic commands first. If this was a regular class during the semester, I would write these two parts as two different labs done on 2 different days, maybe even with a homework in between, so that you can have time to have this sink in and ask questions in between. I'm planning on spending a good chunk of Thursday going over questions from the lab and answering questions about the machine and how it works and stuff like that. So if at all possible, try between now and Thursday morning to get through the part one of the lab, or at least get as far as you can get the part one of the lab before you get stuck. And then come on Thursday with questions, and I will spend as much time as you need, and I'm planning on spending a lot of time helping you guys get through this machine and understand how it works and get you guys unstuck. Okay? This tends to be a relatively hard lab when I teach this face to face. Give yourself time when you're online to have me help you, even though I'm not there to answer questions physically. All right. So now that I've scared you, any general idea questions about this stuff before you go off and see the lab, or what? Seeing none. All right. So try to get to work on this between now and Thursday if you can, so that way I can help you on Thursday, get you unstuck with questions and show you things. I'll try to show you the ideas behind the part two on Thursday as well, so that we can get ahead on that. And that's the plan. All right. So if you don't have any other questions or anything to say, do we have to show working? The more, I mean, yes, in the sense that I really like to see explanations of what you do, especially since if you get it wrong, I can give you partial credit if you have the right idea. If you just type in a number and it's wrong, and I don't know how you got that number, I don't know how to give you partial credit. So explanations always help me know what you know, and it's always a good idea. So yeah, the homework's due tonight. Tonight's fine. Sending it to me by email is fine. I was saying that I don't really care how you do it as long as I can read it. But if you don't care how to do it, sending it to me in like a word processing document that I can put my comments in an obviously different font or color would be helpful. But I can get around it if you don't. If you want to stick it in the body of an email, that's fine. All right, any other questions about this or anything? Okie doke. Then good luck. I will post the stuff to Blackboard today, and I will see you Thursday.